Hello there, and welcome to the Sleepless Scientist, a quiet little place where science slows down and curiosity takes off its shoes for the night. Tonight, we'll drift into one of the calmest, darkest corners of the cosmos, a place so empty it almost hums with silence. But don't worry, it's not a scary kind of emptiness, it's a thoughtful one. A quiet sort of emptiness that stretches like a blank page, waiting patiently for a story to begin. Let's start, not with the distant past, but with something we can actually see, or rather not see. There's a place in the sky called the Bhuta's Void. It lies somewhere near the constellation Bhutas, which, depending on how much stargazing you've done lately, might sound familiar. This void is a staggering 330 million light-years across. To put that into perspective, if our Milky Way galaxy were the size of a grain of rice, the Bhuta's Void would be about the size of a football field. And yet within that enormous space there are hardly any galaxies at all. Just a scattered handful drifting like lonely boats on a silent ocean. Astronomers call it a super void. It's not completely empty, nothing ever truly is, but it's eerily close. So few galaxies, so much nothing. If you looked in its direction with a telescope, you wouldn't see stars blazing or spiral arms stretching across space. You'd see something closer to ink, a dark patch where the usual fireworks of the cosmos are strangely, almost unnaturally absent. It's not a hole, not a black hole or any kind of collapse. It's simply vacant. It's tempting to imagine that the universe was born with brilliant light, like a cosmic light bulb being switched on. But the truth is quieter, more drawn out, more like a room slowly filling with dawn after a long night. The Bhuta's Void is, in a way, a modern echo of the time we'll be exploring tonight. A time even emptier, even quieter, a time before any stars existed at all. This time has a name, the Cosmic Dark Ages, and despite how dramatic that name sounds, they were not terrifying or violent. In fact, they were remarkably still, peaceful even. But in that stillness, something profound was unfolding. To understand the Dark Ages, we need to rewind the universe, not by a few thousand years, not by a few million, but by nearly 14 billion years, to just after the Big Bang. At first, the universe was hot, too hot for atoms, too hot for light to move freely. It was a blinding soup of particles colliding and scattering in every direction. Light couldn't travel more than a short distance without bouncing off something. Imagine being in the middle of a dense fog, but one made of energy, not water. That was the early cosmos. But then, about 380,000 years after the Big Bang, which may sound like a long time, but in cosmic terms is practically yesterday, the universe cooled down. Not cold, but cool enough that electrons and protons could finally settle down and form neutral hydrogen atoms. This moment is known as recombination, though it's a bit of a misleading name since these particles were forming atoms for the first time. When that happened, something beautiful occurred. Light was finally free to travel. Photons, the little packets of light energy, no longer bumped into everything. They could move in straight lines, stretch their legs, so to speak. The result of that freedom is something scientists call the cosmic microwave background. The oldest light we can still detect today. It's like a baby photo of the universe, faded and stretched with time, but still there, still whispering. But that light, as wondrous as it was, quickly faded from visibility. The universe kept expanding. The wavelengths of that light kept stretching, like taffy pulled thinner and thinner until it shifted from visible light into the microwave range. Gentle, cold, lingering. And after that moment, after light broke free, something strange happened. Nothing else lit up. There were no stars yet, no galaxies, just vast, cooling hydrogen gas. Gravity was working, pulling matter slowly into the beginnings of shape. But it was still too early for things to ignite. The sky, if there had been anyone to look up at it, would have been utterly black. That's what we mean by the cosmic dark ages. From about 380,000 years after the Big Bang, all the way to perhaps 200 million years later, the universe existed in a kind of deep, silent dusk. Not dead, not empty, but quiet. A kind of waiting. And that perhaps is the most beautiful part. We often think of darkness as a void, a failure, an absence. But this was a creative darkness, a gestational silence, like soil before the first sprout, like breath before the first word. There was structure forming in secret. There were clumps of matter gathering. There was motion in the stillness. The darkness wasn't the end of something. It was the beginning. If you ever find yourself outside on a cool night, far from the city, under a sky that looks quiet and vast and still, imagine that sky before even the first star was born, before even one spark had broken through. That's where we're going. But don't worry, we'll take it slowly. The universe did too. There's something poetic about the idea of the last light. Not a fading sunset or a flickering candle, but a cosmic light. One that had travelled for nearly 14 billion years just to brush against a telescope lens or the surface of your eye. A light that was born not from a star or a fire, but from the universe itself, exhaling after its first breath. To understand this light, and what came after it, we have to go back, way back. Back to a time when there were no stars, no galaxies, and not even the atoms that would one day build them. The universe was still young then, wild, blazing, too hot and too dense for anything to settle down. In the first few 100,000 years after the Big Bang, space wasn't empty and quiet like it is now. It was packed with energy, a roiling plasma of particles, electrons, protons, photons, all bouncing and colliding like dancers in a too-crowded ballroom. Light at that time couldn't travel freely. Every time a photon tried to go anywhere, it would run into an electron, scatter, and bounce again. It was like trying to move through a fog made of pure energy. The universe, for all its brightness, was not transparent. It glowed, but it was blinding and directionless. A hot, humming blur. Then, something changed. Roughly 380,000 years after the Big Bang, the universe cooled just enough for something quiet but profound to happen. The electrons, once too energetic to stay put, finally began to settle down. They paired up with protons and formed the very first atoms. Simple hydrogen, mostly, and a touch of helium. This moment is called recombination. Though it's a slightly misleading term, these particles weren't combining again. They were doing it for the first time, and yet the word stuck. Perhaps because this event felt like a kind of reunion. Energy and matter finally coming into harmony. And with that, something beautiful happened. Light was set free. When electrons and protons stopped scattering photons, those photons, the ones that had been endlessly ricocheting around the early universe, could finally escape. They could travel in straight lines, unimpeded, released like birds from a cage. This release is what created the cosmic microwave background, or CMB for short, a sea of ancient light that still surrounds us today. It's not visible to the naked eye, but it's everywhere, woven into the fabric of space. If you've ever seen the static on an old television, a tiny fraction of that snow comes from this primeval glow. A whisper of the universe's first calm. The CMB is the oldest light we can see. Not with our eyes, but with radio telescopes carefully tuned to its cool microwave frequency. It is a portrait of the universe as it was in its infancy. Soft, smooth, and almost featureless, except for the tiniest temperature variations, the seeds of all future structure. But while this light was the beginning of transparency, it was also, strangely, the end of brightness, at least for a long time. After that initial release, no new sources of light appeared. The universe was filled with neutral hydrogen, cool and quiet. And though that hydrogen filled space, it did not shine. It didn't emit visible light. It didn't sparkle. It simply drifted. The light from recombination, stretched thinner and colder by the expansion of space, gradually faded from visibility. Once vibrant, it now glowed in microwaves, far beyond what our eyes could detect. The sky, had you been there, would not have looked like a starry dome. It would have looked empty, perfectly, utterly dark. This is the moment when the cosmic dark ages truly began. We often speak about the darkness after recombination, as if it were a tragedy, as if the lights went out and the universe slumped into silence. But that's not quite right. It's more like the lights were never really on in the first place. The brightness of the early universe was trapped, unable to illuminate anything, and when it was finally released, it immediately began to fade. It's hard to imagine a sky with no stars, no galaxies, no glimmering planets. But for hundreds of millions of years, that was reality. A universe made of hydrogen, dark matter, and time. Waiting. And yet, that waiting wasn't pointless. The silence after the first light gave space, both literal and figurative, for structure to form. The hydrogen that drifted in this darkness began to gather under gravity's quiet pull. Invisible threads of dark matter shaped the paths along which normal matter would fall. Tiny fluctuations in the density of the gas began to grow, imperceptibly at first, but steadily. This was the silent prelude to everything, to stars, to planets, to galaxies, even to you. And the light that had filled the universe at recombination, though it had faded, had not disappeared. It's still here. It just changed. As space expanded, that light was stretched along with it. Its waves lengthened, moving from the visible spectrum into the infrared, then into microwaves. What once may have been a bright, brilliant white light became a gentle, uniform background hum, detectable only by sensitive instruments. Not gone. Just red-shifted. Time transformed brightness into depth. So when we point our telescopes to the sky and try to understand what came next, the formation of the first stars, the rise of structure, the end of the dark, we're always working in the shadow of that moment. The last light before silence. It wasn't a flash. It was a release. Not a farewell, but a beginning. A light that lingered and then faded into silence. And in that silence, the universe began preparing something extraordinary. In the darkness, something was already at work. It wasn't light because light had faded. It wasn't atoms because atoms were still drifting, cool and unhurried. No, what shaped the universe during this silent age wasn't anything we could see. It was something deeper, something stranger, and something that to this day has never revealed its face. We call it dark matter, not because it is shadowy or sinister, but simply because it doesn't shine. It doesn't glow or shimmer or reflect. It doesn't absorb light or radiate heat. It passes through space, through galaxies, even through us, without so much as a flicker. But it's there, and it holds everything together. Imagine, if you will, that you're floating in the early universe. There are no stars yet, no planets, no glowing dust or twinkling galaxies, only an ocean of hydrogen and helium, stretched across a vast canvas. But beneath that ocean, beneath the visible, lies a hidden scaffolding. It doesn't sparkle, it doesn't move in ways your eyes can follow, but it has mass, and it pulls. That pull, gravity, is the only way we know it exists. And yet, that quiet, invisible tug has shaped everything. In the earliest moments after the Big Bang, dark matter was already forming slight clumps, tiny overdensities, just a little more crowded than the regions around them. Over time, as space expanded and cooled, these clumps grew. They didn't glow, they didn't ignite, but they pulled. And what they pulled was the regular matter, the protons and electrons that had just begun to form neutral atoms. While the hydrogen gas drifted slowly through space, it was being drawn towards something it couldn't sense, something silent. The dark matter halos, small at first, but growing. began to gather gas into their centres, like seeds pulling soil around themselves, like roots digging through unseen earth. This was the beginning of structure, not in the way we think of structure on Earth, with beams and buildings and blueprints, but in the cosmic sense. Clumps became clouds, clouds formed halos, halos grew dense enough to trap heat, and heat in time would lead to ignition. But all of this depended on a backbone that never showed itself. We know dark matter is real, not because we've seen it directly, but because we've seen its effects. The way galaxies spin, too fast, as though something unseen is holding them together. The way light bends around clusters of galaxies, distorted by the gravitational presence of mass that isn't there. The way the universe formed its grand web-like structure, with filaments and voids, nodes and connections, as though something had been drawing it with invisible ink. Simulations of the early universe, vast complex models run by supercomputers, show us how essential dark matter was. Without it, the hydrogen gas would have remained too smooth, too slow. It would never have gathered in time to form stars or galaxies. The universe, beautiful as it might have been, would have stayed dark far longer. But with dark matter as its guide, the gas found its way into the deep gravitational wells that were waiting. And as more matter fell in, the wells grew deeper, a kind of cosmic feedback loop. More pull meant more mass, and more mass meant more structure, and all of it in silence. There is a strange comfort in knowing that the universe was being shaped by something it couldn't see, that even in the absence of light, there was already a pattern, a rhythm, a structure. The stars would come later, but the framework that would hold them, that had already begun. We call it a cosmic web, an enormous network of filaments stretching across billions of light years. Between these threads lie voids, vast, nearly empty regions, and within the nodes, where the filaments intersect, galaxies would eventually bloom. But the web itself is made not of starlight or nebulae. It's made of dark matter, quiet, invisible, essential. It's strange to think that we owe our existence to something we've never truly seen, that the atoms in your body, in your breath, in your thoughts, were drawn together not by light, but by gravity. And not even the gravity of things that shine, but of things that don't. Dark matter doesn't just hold galaxies together, it made galaxies possible in the first place. And so, while the universe looked quiet, even empty, something was already happening beneath the surface. A silent architecture was unfolding, not with explosions or bright edges, but with the soft, persistent pull of mass across time. It's easy to overlook that kind of presence. We're trained to pay attention to what glows, what sparkles, what makes noise. But the universe doesn't always work that way. Sometimes, the most important things are the ones that stay in the background, shaping, guiding, holding steady, while the stars prepare their entrance. And if we could float there, through the darkness, we might not see the filaments forming, but we would feel them. Not as a rush or a tug, but as a direction. A sense that some places were heavier than others, that some corners of the sky were beginning to fold in on themselves, preparing for the light. The stars were not yet born, but the paths they would take were already written, not in fire, but in gravity. If dark matter was the scaffolding, the invisible skeleton guiding the universe's shape, then hydrogen was the breath that filled the lungs. It was the atmosphere of creation, the canvas on which light would one day be painted. But for millions of years it remained still, vast, undisturbed, and so profoundly simple, it's easy to miss just how essential it was. After recombination, that moment when electrons and protons first settled into neutral atoms, the universe was filled almost entirely with hydrogen gas. Not the kind of hydrogen you might find in a balloon, or inside a star, energized and restless, but something much quieter. This hydrogen was cool, gentle, dispersed in every direction like fog rolling over a field at night. It didn't shine, it didn't flare, it didn't gather in dense clouds or orbit burning stars, not yet. Instead, it formed a smooth, nearly uniform sea, stretching across the universe in every direction. There were no storms in this ocean, no waves crashing or swirls of current. Just an extraordinary calm, spreading out through space like a breath being held. But this stillness was not lifeless. It was preparation. You might imagine it like the surface of a lake just before dawn. Everything is still, perfectly still. But beneath that surface, subtle motions have begun. The water shifts, a ripple begins, and somewhere, far below, something is rising. That's what the hydrogen was doing. Slowly, patiently, waiting for gravity to give it direction. Though we often think of gas as something wild, chaotic, uncontrolled, the hydrogen of the early cosmos was astonishingly well behaved. The temperature dropped after a combination, and without stars or galaxies to stir it, it remained largely undisturbed. It was, in some ways, the simplest the universe would ever be. And yet, within that simplicity lay immense potential. Everywhere you looked, in every corner of the sky, in every direction, there was hydrogen. And although it was mostly uniform, there were tiny variations, minute differences in density, in temperature, in motion, so small they might seem meaningless. But over time, they would grow. And that's the key. Time. Time was the great partner in this story, because nothing happened quickly. There were no explosions, no sudden collapses, only slow accumulation. The slightly denser regions of hydrogen, just a bit more crowded than their neighbours, would begin to pull in more gas. Gravity, always patient, began to do its work. The cold hydrogen, ever cooperative, followed. This wasn't a process of days or weeks, not even of millions of years. It was a process that unfolded across hundreds of millions of years, a story told in geologic stillness and cosmic restraint. But it was a story all the same. Hydrogen's simplicity is what made it so powerful. It had only one proton, one electron, the lightest and most abundant element in the cosmos. Yet with time, and the guiding hand of gravity, it would become the fuel for everything. For stars, for galaxies, for chemistry, for life. And during the cosmic dark ages, it filled space not like a gas rushing outward, but like a still pond slowly deepening. Scientists call this period one of homogeneity, a time when the universe looked almost the same in every direction. But even that term can be misleading. It doesn't mean boring. It doesn't mean meaningless. It means that things were calm enough, smooth enough for the laws of physics to begin shaping complexity. Think of a painter preparing a canvas. Before the first stroke of colour is added, the surface must be even. The base must be smooth. The hydrogen-filled universe was that base. Silent, wide, uncomplicated, and yet brimming with this potential for stars. But here's something curious. Even though hydrogen didn't emit visible light, it wasn't completely mute. It had a voice, a whisper, a kind of memory tucked inside its atom, waiting for the right instrument to hear it. Each hydrogen atom, as simple as it seems, contains a proton and an electron. And like tiny spinning tops, each of these particles has a property called spin. Sometimes their spins align in the same direction, and sometimes in opposite ones. And when an atom flips from one configuration to the other, a process that happens rarely, quietly, but with mathematical precision, it emits a tiny burst of radio energy. This is the 21 centimetre line, a signature signal from hydrogen that we'll explore more deeply in sessions ahead. For now, what matters is this. Even in the dark, hydrogen was preparing to speak, not loudly, not often, but enough. Enough that billions of years later, scientists with radio telescopes would begin to listen for those tiny signals, and through them, map the vast ocean that once filled everything. An ocean we'll never see, but whose ripples still reach us, This is the strange beauty of the cold dark ages, a time when the universe was neither dead nor chaotic, just quiet, patient, alive with potential. Hydrogen didn't need to shout, it just needed to be there, everywhere, ready for gravity to nudge it into place, and eventually for heat and collapse to coax it into fire. The sea was calm, but it was deep, and soon it would begin to rise. There's something quietly magical about pointing a telescope at a patch of sky that looks completely empty, and waiting. In the 1990s, scientists using the Hubble Space Telescope did something that, to many, seemed like a waste of precious time. They turned the telescope, one of the most powerful optical instruments humanity had ever launched, toward a tiny, unremarkable patch of the sky. A patch so small it was like peering through a drinking straw. And not only that, they pointed it at a region that appeared to contain nothing. No bright stars, no clusters, just darkness. But they waited. Over the course of several days, Hubble collected faint photons from that darkness, letting them pile up gently like snow. And what it revealed became one of the most iconic images in the history of astronomy. Thousands of galaxies. Not stars, galaxies. Each one filled with billions of stars of its own, some larger, some smaller than our own Milky Way. Packed into a region of sky that, from Earth, looks like a blank whisper. That image became known as the Hubble Deep Field, and later, the even deeper ultra-deep field. It was a revelation, a sudden reminder that the universe is not mostly empty, it's mostly hidden. But even Hubble, for all its brilliance, has a limit. Light doesn't just travel across space, it stretches. As the universe expands, light waves moving through it also stretch, like taffy being pulled by invisible hands. This means that the farther away an object is, and therefore the older the light we receive from it, the more its light has been shifted toward longer wavelengths, redder, cooler. Eventually it shifts right out of the visible spectrum altogether, sliding into the infrared and then beyond. This shift is known as redshift, and it places a kind of boundary on our cosmic vision. There's a point beyond which light becomes too stretched, too faint, too distant for our eyes, or even for Hubble's, to detect. To look further, we had to build a new kind of eye. In 2021, NASA launched the James Webb Space Telescope, JWST, designed to see in infrared, the longer wavelengths where ancient light now lives. With its golden mirrors and delicate sunshield, Webb was built to peer back deeper in time than anything before it. Not to see stars as they are now, but to glimpse them as they were billions of years ago, when the universe was still assembling its first structures, and already it has delivered. Galaxies from a time when the universe was less than 1 billion years old, complex structures emerging where once we thought there would only be smudges, star nurseries blooming in rich detail. It's like someone turned up the contrast on the cosmos. But even JWST has its limits. No matter how sensitive our instruments become, no matter how long we stare into the void, we can't see past a certain point. Not because we lack the tools, but because light itself had not yet been born. Before the first stars, before the first galaxies, there was no light to see, only hydrogen, only darkness. And so, while Hubble and Webb allow us to look back through space and time, there comes a point, a hard, undeniable horizon, beyond which sight fails us. And that's where the story takes a quiet turn. If we cannot see the early universe, perhaps we can listen to it. That idea might sound strange at first. After all, space is a vacuum. There's no air, no medium to carry sound in the way we experience it on Earth. But listening, in the language of astronomy, doesn't mean hearing in the traditional sense. It means detecting waves, not of pressure, like sound, but of electromagnetic energy, at frequencies our eyes are blind to. And one of the most important frequencies, one that predates starlight, that pierces even the earliest darkness, is not in the visible range at all. It's a whisper, a wavelength, 21 centimeters long, invisible to our eyes, but not to radio telescopes. This is where the next chapter of cosmic exploration begins, not with optics, but with antennas, not with glass and mirrors, but with instruments that can pick up the faintest size of the universe's hydrogen. Because while Hubble showed us what lay hidden in apparent emptiness, and JWST pushed that boundary further still, both are ultimately limited by the same truth. Light has a beginning. And before that, we must stop looking and start listening. It's a humbling realization. We often think of vision as the most powerful sense, as something absolute. But the universe reminds us again and again that what we see is only a fraction of what exists. That most of reality lies just beyond the spectrum we perceive. That sometimes, to understand the earlier stories, we have to tune in, not zoom in. In the next session, we'll explore this strange 21 centimetre signal, where it comes from, why it matters, and how it became one of the most valuable clues to a time we cannot see. But for now, let's rest in the knowledge that the darkness isn't empty, it's just waiting to be heard. When everything is dark, and the stars have not yet formed, it may seem as though the universe has nothing more to say. But sometimes, silence isn't a lack of sound. It's a message in a different language. The early universe, wrapped in cool hydrogen and quiet gravity, was already speaking. It just wasn't speaking in light. It was speaking in a wavelength, a signal too soft for the eye, but unmistakable to a patient ear. This signal is called the 21 centimetre line, and it is one of the most important whispers the cosmos has ever produced. The story of this line begins not with telescopes or rockets, but with a young Dutch physicist named Hendrik van der Hulst. In 1944, during the Second World War, van der Hulst was just a graduate student, working under the shadow of occupation, reading physics journals and wondering what secrets hydrogen might still be hiding. At the time, the atom had been studied extensively, but van der Hulst noticed something subtle, something that had been largely overlooked. Hydrogen, the most common element in the universe, consists of just two parts, a proton in the centre and an electron orbiting around it. Both the proton and the electron have a property called spin, a kind of intrinsic angular momentum. In most hydrogen atoms, the spins of the proton and electron are aligned in the same direction. But sometimes, almost by accident, the electron flips, so its spin points in the opposite direction to the protons. This tiny flip, though seemingly insignificant, causes the hydrogen atom to release a tiny burst of energy, not in the form of visible light, but as a radio wave, specifically with a wavelength of about 21 centimeters, or a frequency of 1.42 gigahertz. It's an extraordinarily faint signal. A single atom might go millions of years before flipping. It is the softest of murmurs, so soft that van der Hulst himself was unsure whether anyone would ever detect it. But he predicted it anyway, and in doing so he opened a doorway into the past. Because hydrogen is so abundant, and because this transition occurs wherever neutral hydrogen exists, the 21 centimeters line is emitted across the cosmos, not in brilliant flashes, but in a steady background hum. A slow, persistent rhythm. And most importantly, because this radiation travels through space largely unaffected, it can reach us from regions and times far beyond what light can reveal. This makes the 21 centimeters line perfect for exploring the cosmic dark ages. Unlike light from stars, which only begins to shine after the first stars ignite, the hydrogen line was being produced during the long cold silence before them. It's not strong, but it is old. It predates galaxies. It predates light. It's one of the only traces we have of that quiet ocean of gas that filled the young universe. But here's what makes it even more remarkable. As the universe expands, it stretches space itself, and with it, it stretches all the waves travelling through that space. This means the 21 centimeter line, though emitted at a fixed frequency, arrives at Earth at different wavelengths depending on how long it has been travelling. A more distant hydrogen cloud, one from earlier in time, we'll have a more redshifted signal than one closer to us. And so, by detecting and analysing these different stretches, scientists can effectively map hydrogen across time. It's like listening to an echo in a canyon, not just hearing the sound, but being able to tell exactly how far each surface is based on how the echo bends and fades. This is why radio telescopes that are tuned to 21 centimetres, or more precisely, to the redshifted versions of that signal, are some of the most powerful tools for studying the ancient universe. They don't show us images, not in the way we're used to. Instead, they give us slices of history, one thin layer at a time based on frequency. Each observation reveals what the hydrogen was doing at a different age. And in those layers, scientists can look for the earliest signs of change, regions where the hydrogen is slightly warmer or cooler, denser or more spread out. These are the signs that something is stirring, that the silence of the dark ages is about to break, that stars are forming, galaxies are beginning to take shape, and the first light is preparing to return. But long before any of that, the hydrogen was already singing, quietly, consistently, patiently. It's astonishing to realise that this line, the 21 centimetre signal, predicted in a war-torn Europe by a young scientist with nothing more than paper, chalk and curiosity, would become one of the most sought-after clues in modern cosmology. And it's even more astonishing to know that this line is everywhere. When you look up at the night sky, you might see stars, or perhaps just a soft wash of darkness. But beneath that, behind it, threaded through it, there is this signal, not one bright enough to be noticed, not something your eyes could ever detect, but there, all the same, a hum, a memory, a trace of a time before light still reaching us. It's as though the universe in its earliest stillness left us a note, not to dazzle us, not to impress, but simply to remember, to offer a record of how it once was, before it became what it is. A line too, quiet for eyes but loud to a tuned ear, and we are listening now. When we think of a map, we usually imagine something visual, a coastline drawn in delicate curves, a trail winding through forests, the hard lines of cities, borders and rivers. Maps speak of places, tangible, visible things. But what if a map could be made from soundless signals, from whispers that have travelled for billions of years? What if a map could describe not what we see, but what once existed in darkness, long before light ever showed the way? That is what the 21 centimetre hydrogen line allows us to do. The signal itself, as we've learned, is born when a near-electron flips its spin in relation to the proton it orbits. A quiet event, but one that repeats throughout the universe whenever neutral hydrogen is present. And because hydrogen was everywhere during the cosmic dark ages, so too was this faint radio emission, scattered across space like a forgotten song. But the true magic happens when we listen to this line at different frequencies. As the universe expands, it stretches the space between objects. This means that waves, including radio waves, get pulled along with it. The 21 centimetre signal, originally emitted at a specific frequency, becomes redshifted as it travels through space. And because older signals have travelled longer, they are stretched more. The longer the journey, the longer the wavelength becomes. This stretching becomes a kind of cosmic timestamp. By measuring the frequency at which a 21 centimetre signal arrives, astronomers can calculate how far it has travelled and therefore how old it is. It's not just that we're listening to hydrogen. We're listening to hydrogen from different times, layered like pages in a book that was written slowly and without ink. And by doing this over many different directions and frequencies, we can start to build something extraordinary, a three-dimensional map. Not of stars, not of galaxies, but of the hydrogen that would one day become them. Each frequency reveals a slice of space at a particular time, like a cross-section through the universe's past, and within each slice the intensity of the signal can vary slightly. Some regions are a little warmer, a little brighter in radio, while others are cooler or quieter. These variations tell us about density, where hydrogen was clumping, where it was thinning, where it was beginning to collapse under gravity's pull. The term scientists use is brightness temperature. It sounds a little odd, because it's not a measure of heat in the traditional sense. Instead, it refers to how strong the radio signal is, and by extension, how much hydrogen is present and how it's behaving. A brighter spot in the map might mean a denser cloud, a region where matter is starting to gather. A dimmer region might be more diffuse, a place still waiting to form structure. And with enough observations, across enough frequencies, in enough directions, these tiny brightness variations become a kind of cosmic fingerprint, a pattern, a scaffold, a time map drawn in static. This process is still incredibly difficult. The 21 Kilometer signal is faint, easily drowned out by nearer sources of radio noise. Not just distant galaxies, but human technologies, satellites, and even the Earth's own atmosphere. Extracting the early universe signal from all that clutter is like trying to pick out the rustle of a single leaf in the middle of a thunderstorm. But the potential reward is staggering, because in that static is a story of formation. We're not just detecting the presence of hydrogen, we're watching it begin to change. We're observing the first ripples of structure, long before stars flicker on. These maps can show us how the universe's geometry began to form, not in the sense of triangles and circles, but in the vast lattice of space itself, the filaments and voids, the dense knots and quiet stretches. What's especially haunting is that these maps show us things that didn't yet shine. They map what isn't there, yet. Not stars, not galaxies, not glowing clouds, but the matter that would eventually become all of those. It's a portrait of the pre-light universe, captured not through sight, but through the memory of waves. Imagine looking at a blueprint not of a finished cathedral, but of a field where stone is just beginning to be laid, where scaffolding is invisible to the eye, but detectable to the hand. That's what these hydrogen maps are. They show us not the stars themselves, but the dark rooms where stars are about to be born. This kind of cosmic archaeology is breathtaking in its ambition. Each data point in the map corresponds to a place, a moment, a condition. Brighter spots become clues. Here, matter was gathering. There, it was still drifting. Elsewhere, it was cooling. And as more data pours in from new experiments and more sensitive instruments, the resolution improves. The static becomes sharper, the whispers become clearer, the shape of what once was, and what would be, begins to emerge. It's a gentle reminder that not all maps are made of roads and rivers. Some are made of time, some are drawn with temperature and echo rather than colour and line. Some are written in the silence before the music begins, and through them, hydrogen, so often dismissed as empty, simple, quiet, becomes our storyteller. Not in speech, not in bursts of fire or sound, but in the steady, stretched-out signals of a time when the universe was still finding its voice. By this point in the universe's story, the silence is no longer empty. It hums, not with music or voices, but with the quiet pressure of gathering. The hydrogen gas that once floated in calm equilibrium stretched evenly across the vastness of space is no longer as still as it once seemed. Underneath its surface, something has begun to stir. And it's not chaos, it's direction. The force behind that direction is gravity. Not the sharp gravity that pulls an apple from a tree or bends your knees when you stand, but something slower, deeper, and older. This is the gravity of dark matter, which, though invisible, had already begun to lay down a skeletal framework for the cosmos. Where its filaments coiled through space, neutral hydrogen began to drift inward, softly but with inevitability. This moment, the beginning of collapse, was not violent or sudden. It was gentle. It unfolded over millions of years. The hydrogen didn't rush toward these dark matter structures. It leaned toward them, like mist drawn to a valley. The differences in density were still minute, but gravity over time is persistent. It doesn't need drama to make its mark. It only needs time and patience. And the universe, in these early days, had plenty of both. As hydrogen gas began to accumulate along these invisible scaffolds, it grew denser in certain regions. With density came pressure, and with pressure the temperature began to rise, but not wildly so. These were the quietest beginnings imaginable. Not fire storms, but the earliest whispers of structure. The hydrogen wasn't yet forming stars, but it was preparing to. Astronomers call these regions halos, spherical gatherings of matter centered around dark matter clumps. They are the first architectural features of the universe. Think of them like basins in a landscape, slowly filling with rainwater. Some would fill quickly, becoming rich pools of material. Others would stay shallow. But all of them were sculpted by the same hand, gravity, and filled with the same breath, hydrogen. And it's here that the 21 centimetre signal becomes more than just a map. It becomes a symphony of compression. As the gas falls into these halos, it experiences changes in velocity and temperature. These spin-flip emissions from hydrogen atoms, the ones producing that precious 21 centimetre radiation, begin to change too. Slight shifts in the frequency and intensity of the signal can tell us where hydrogen is cooling, where it's heating, where it's moving. By analysing the spectral shape of the signal, its depth, its width, its profile, scientists can identify the fingerprints of these early collapses. Even before stars form, the structure of their nurseries is beginning to leave traces in the background radiation. It's almost poetic. Long before light returns, the silence becomes textured. A flat canvas is being folded, softly, patiently, into the first dimensions of cosmic complexity. The hydrogen is not being erased or consumed yet, it is being rearranged. What was once nearly uniform is now taking on form. But what does that form look like? In modern simulations, elaborate computer models of early cosmic evolution, these halos appear as glowing nodes along filaments of dark matter. They form a cosmic web, not unlike the interconnected threads of a spider's design. Where the threads meet, halos appear. The densest ones grow faster. They are the seeds from which galaxies will eventually bloom. The 20 observations, difficult, noisy and delicate, provide the earliest empirical evidence for these structures, not through light, but through absence and motion. Through tiny fluctuations in radio brightness, we hear the gas folding inward. The first creases in space, long before stars illuminate them. One of the strangest things about this process is that it happens in total darkness. There is something deeply moving about that the greatest transformation in the early universe, the beginning of structure, the formation of halos, the quiet movement of gas, all unfolded in a place that no light had touched. The physics was working, the rules were holding, the dance was underway. But no one watching from inside that moment, had there been an observer, would have seen anything at all. Only after enough hydrogen collapses and compresses will the first stars ignite. Only then will light return. But by the time that happens, the universe will have already chosen its architecture, the locations of galaxies, the depths of cosmic voids, the shape of the sky as we see it today. So in a way, we are not made just of stardust. We are made of decisions made before stars. The early universe didn't just set the stage, it built the stage. In the folds of hydrogen, in the gravity of dark matter, in the invisible collapse of halos waiting to shine. And the 21 centimetre line, faint as it may be, is the memory of that building process. When we tune our radio telescopes to the right frequencies, when we filter out the close noise and amplify the ancient echoes, we begin to hear those collapses. Not loudly, not clearly, but enough. Enough to say, here. This is where the quiet began to bend. This is where stillness started to move, and in that movement, a story began. For hundreds of millions of years, the universe had been a sea of stillness. There were ripples, yes, of gravity pulling hydrogen into halos, of faint signals stretching across space, but there was no light. Not the kind that sparkled, not the kind that warmed. There was only motion without flame, structure without radiance. Until one day, in the deeper silence, a star was born, and then another, and then many. These were not stars like the ones we see today. They were something far more ancient, far more raw. Astronomers call them Population 3 stars, a name that might sound clinical, but behind it lies something almost mythic. These were the first stars to ever shine, formed from the original ingredients of the cosmos, hydrogen and helium, nothing more. They had no metals, no carbon, no oxygen, no iron. In astronomy, any element heavier than helium is called a metal, and these stars had none. Their birth clouds had never known the death of a previous star. They were pure, untouched by time, unshaped by anything except gravity and primordial gas. And because of that, they burned differently. Population 3 stars are thought to have been enormous, many times the mass of our Sun, perhaps even hundreds of times heavier. And with that mass came heat. Intense, unimaginable heat. Their cores fused hydrogen at a furious pace, releasing torrents of ultraviolet radiation that flooded their surroundings. These stars were bright, not just in visible light, but in the high-energy wavelengths that would reshape the very structure of the universe around them. But for all their brilliance, they were also short-lived. A few million years at most, the blink of an eye on cosmic timescales, and then they were gone. Some may have ended in supernovae, exploding in violent flashes that spread the first heavy elements, carbon, oxygen, iron, into space. Others may have collapsed directly into black holes, slipping silently into the fabric of space-time. But whether they ended with a bang or a whisper, they left behind a changed universe. Because for the first time since recombination, the universe was no longer dark. The light from these stars didn't just illuminate space, it began to shape it. Their ultraviolet photons had enough energy to strip electrons from hydrogen atoms, a process called ionization. In doing so, they transformed the cold, neutral hydrogen that had filled the cosmos into a hot, ionized gas that could no longer hold onto its electrons. This transformation didn't happen all at once. Each star created a kind of bubble around itself, a sphere of ionized gas expanding outward into the neutral hydrogen beyond. At first, these bubbles were isolated, like lanterns flickering in a fog. But as more stars formed and more bubbles grew, they began to overlap. The fog began to lift. The dark began to give way. This is the beginning of a period cosmologists call the epoch of reionization, a grand, slow transition from darkness to light. But that comes in the next session. For now, let's linger here, in this early moment when light returned for the first time. It's strange to think that these first stars are gone. We will never see them directly. Their light has long since faded. Their explosions, if they happened, have already swept their way through space. But we know they were there, not from direct images, but from their effects in the chemistry of later stars, in the structure of galaxies, in the ionized gas we now see across space. They may not have lived long, but they were essential, because everything that came after, every planet, every galaxy, every breath of air, every thought you've ever had, was built on the ashes of those first fires. They were the ones who lit the match. They burned alone, in silence. They were not seen, but they changed everything. The first stars did more than shine. They disrupted. Their light, while beautiful in theory, wasn't a gentle glow on the surface of space. It was transformative. The ultraviolet radiation pouring from those early population 3 stars was sharp, powerful, and relentless. It didn't simply pass through the cosmos, it changed the state of the cosmos itself. In every direction, the darkness wasn't merely lit, it was carved. To understand this, we need to return to hydrogen, the same cold, neutral hydrogen that had filled the universe for hundreds of millions of years. It had been still, patient, almost passive, until gravity began to gather it, until stars arrived. And with stars came ultraviolet light, radiation strong enough to knock electrons loose from those once settled hydrogen atoms. This process is called ionization. One high-energy photon slams into a neutral hydrogen atom and liberates its electron. What's left is a positively charged proton and a free electron no longer bound together. The gas is no longer neutral, it's ionized. This changes everything about how the gas behaves, how it interacts with light, how it cools, how it collapses. Ionized gas is more active, more transparent, more influenced by radiation. But this didn't happen everywhere at once. Each of those first stars, scattered across the universe like isolated campfires, began by ionizing a small sphere of space around itself, a glowing bubble of altered gas. These spheres, or ionized regions, slowly expanded as more ultraviolet light streamed out. For a long time, they remained separated, like dewdrops on a spider's web, isolated, glowing, but distant. And yet, with each new star, more bubbles appeared, and with time, they grew. The expanding spheres of ionized gas started to touch, to overlap, to merge. The stars may have been brief, but their collective influence accumulated. The once neutral universe began to resemble a kind of foam, dark hydrogen interspersed with spreading pockets of brightness, of activity, of change. Each bubble was a hole in the darkness, torn open not with violence, but with photons, the smallest particles of light moving with quiet purpose. This slow process, playing out over hundreds of millions of years, marked the beginning of what cosmologists call the epoch of reionization. It's a long name for what is, at its heart, a simple transformation. The universe relearning how to shine. Reionization doesn't refer to one specific event, or even to one specific time. It's a chapter, one that begins when the first ionized bubbles appear, and ends when they have merged and spread so thoroughly that the universe becomes transparent again. Because before this, even though the universe had cooled enough to form atoms, and even though light could technically move through it, much of that light was scattered, absorbed, redirected. The neutral hydrogen was opaque to many wavelengths. But once the hydrogen became ionized, space became clearer, more open to light, more navigable. This is why we often speak of reionization as lifting a fog. It's not just that light appeared, it's that light could finally move freely. The echoes of this transition are still visible today. When we observe the light from distant quasars or galaxies, we can sometimes see absorption features in their spectra, signs that their photons pass through patches of neutral hydrogen. These signatures help scientists determine when reionization occurred, and how complete it was at different moments in time. The more opaque the universe at that redshift, the earlier it is in the reionization process. And of course the 21 centimeter hydrogen line continues to help us here too. As neutral hydrogen becomes ionized, it stops emitting that faint spin flip signal. So as the universe transitions from mostly neutral to mostly ionized, the 21 Sigma signal fades. By mapping when and where that signal disappears, astronomers can track the progress of reionization, like watching streetlights turn on one by one until the entire city is lit. But it's important to remember that this light was not uniform. The first stars did not appear everywhere at once, nor did reionization proceed in a smooth, even way. It was patchy, shaped by the uneven distribution of matter and the uneven timing of stellar births. Some regions reionized early, others late. Some remained neutral long after others had cleared. It was a cosmic patchwork, a slow undoing of the long silence, woven star by star. What's remarkable is how this chaotic, uneven process led to such an elegant, transparent universe, the one we now see. The stars didn't just make things brighter, they made things clearer. They didn't simply decorate the sky, they opened it. And though none of those first stars remain, their work endures. Every time we gaze at the sky and see through the blackness, we are looking through holes they carved, windows they opened. There's something quietly poetic about that. Stars didn't just shine, they tore holes in the dark. They punctured silence with memory. And in their wake, they left a sky we could finally see through. Reionization is a word that sounds sharp, almost clinical, but the reality it describes is far more delicate. A slow, shimmering undoing of darkness that took hundreds of millions of years. There was no sudden blaze, no moment when night turned to day. Instead, there was a mist, a cosmic fog that lifted not with a flourish, but with time. By now, the universe had entered its adolescent years. The first generation of stars, massive and short-lived, had already come and gone, leaving behind metals, heat and momentum. New stars began to form in greater numbers, not as enormous as the originals, but more numerous, more enduring. Galaxies emerged like slow ripples in a pond. Collections of stars and gas clustered along the filaments of dark matter. Some burned quietly, others blazed, and some, in the densest places, birthed quasars, luminous beacons powered by supermassive black holes, devouring matter at their cores and flooding space with radiation. These were the new architects of change, not alone, but together. With every newborn star, with every growing galaxy, they became the weavers of a new transparency. As more galaxies ignited, each brought with it another ionized bubble, another patch of cleared sky in the vast ocean of neutral hydrogen. These bubbles, like the earliest ones before them, started small, but unlike before, they no longer remained isolated. With more sources of ultraviolet light, the growth of each bubble accelerated, and as they expanded, they merged. The universe became a patchwork of ionized and neutral regions. Picture a foggy plain in the first hours of dawn, with pools of sunlight spreading slowly from scattered clearings. There's no single sunrise, just a thinning, a quiet breath in. The haze begins to lift, not everywhere, not all at once, but enough. This unevenness is important. Reionization was not a switch being flipped, it was a slow dissolution. Some regions reionized early, near dense clusters of galaxies. Others stayed neutral much longer, shielded by distance, emptiness, or lack of luminous neighbours. The timeline was messy, but the direction was clear, and so, over the course of hundreds of millions of years, the fog retreated. It's worth pausing here to understand what that fog truly was. It wasn't vapour or smoke. It wasn't something you could see. But it was real. A veil made of neutral hydrogen, stretched across space. This hydrogen wasn't dark in the way we think of shadows, but rather opaque to certain kinds of light. Photons, especially in the ultraviolet and visible ranges, couldn't travel far without being absorbed or scattered. The early universe may have been full of stars, but from most vantage points it was still cloaked in murk. That's what the ionizing light changed. Every photon that stripped an electron from hydrogen cleared a small piece of the veil. Every new star was another tiny opening, and though each one was small, together they began to tip the balance. Eventually, the majority of hydrogen in the universe became ionized. The fog, once thick and total, became thin, then patchy, then almost gone, and what had once been a shrouded world became a transparent one. This transparency is more than a physical change, it's an observational gift. Only after reionization do photons travel across the cosmos freely. Only then do they reach our telescopes without interference. The galaxies we study today, in deep field images, in JWST infrared snapshots, are visible because they live in a universe that was made clear by this long process. The fog cleared not for us, of course, but it's because it cleared that we are able to look so far, so deep, and see the universe as it was long before we arrived. It's also why there's a kind of soft edge to our vision of the past. We can peer back to a time just before reionization ended, but not much further. Before that, the fog thickens, the light fades, the photons we seek are blocked, scattered, or never reach us at all. This is the cosmic curtain, not of time, but of transparency, and reionization is the slow pulling back of that curtain. In this way, the universe's early fog was not just a barrier, it was a story in slow erasure, a hush being replaced by quiet breath, a long inhale before the first clear exhale. And when we now look into that clarity, when we gaze at stars that lived billions of years ago, or see galaxies as they were when the Earth was still a dream, we're seeing through the spaces carved by countless photons long since gone, but still shaping what we're allowed to witness. It wasn't a sunrise, it was a shimmering mist, and now it's almost gone. There is a special kind of quiet that comes just after fog has lifted. The shapes that were once softened begin to sharpen. Distances stretch a little further. The world does not necessarily become louder, but it becomes more real, more knowable, and in much the same way, after hundreds of millions of years suspended between silence and illumination, the universe became, finally, transparent. This moment, or rather this long era drawn to a close, did not arrive with fanfare. There was no clear signal, no universal announcement. But the change was profound. The epoch of reionization, that slow and patient erosion of the neutral hydrogen fog, had come to an end. By this point in cosmic history, most of the hydrogen in the universe had been ionized. The stars, once rare and scattered, now burned in galaxies across the sky. Their light was no longer stifled or scattered. It could travel freely, unimpeded, across the expanding canvas of space. And for the first time, the cosmos could see itself. It's easy to take this transparency for granted. We live in it. Our entire vision of the universe, everything we know about galaxies, clusters, and the vast web of cosmic structure, relies on it. But for most of the universe's life, this openness did not exist. In its earliest chapters, space was either too hot and dense for light to move, or too full of neutral hydrogen to allow light to pass through cleanly. Photons were constantly colliding, bouncing, absorbed and re-emitted, lost in a fog that filled every corner. Once reionization completed, that changed. The sky became optically thin, a technical term but one that captures something surprisingly poetic. It means that light could move across space without being blocked. It could stretch, bend, redshift, but not disappear. It could carry stories of stars, of explosions, of galaxies forming and merging, and deliver them across unimaginable distances. The sky, once murky and flat, now had depth. You might imagine standing on a mountaintop before dawn, looking out at a land covered in mist. Everything feels close and muffled. But then, as the fog lifts, the valley below appears. Trees, rivers, distant ridgelines. The world expands outward. Not because anything has moved, but because now you can see. The universe did the same. It didn't change in shape, but in legibility. It became a place where light could leave one galaxy and travel across space, and time into another, into ours. This transparency also marks the beginning of the observable universe as we truly know it. Before reionization, what little light existed couldn't reach us. But after, light from galaxies, stars, supernovae, and eventually quasars could begin their long journey toward us, forming the cosmic fossil record that our telescopes now read like ancient scrolls. It also means that cosmic structures, once hidden, could be revealed. The large-scale filaments of matter, the voids between them, the formation of clusters and superclusters, all of this became visible through the light that now traversed space with ease. Observatories like the Hubble Space Telescope, and more recently the James Webb Space Telescope, take advantage of this gift. They peer across billions of light years, and thus billions of years in time, to capture galaxies as they were when the fog had only just cleared. In fact, when astronomers say they're looking at the earliest galaxies, they're often seeing light from just after the end of reionization, those first stars and galaxies whose light was no longer buried in mist, but finally free to wander. That light took over 13 billion years to reach us. It survived a journey through space that was itself stretching as it travelled, and yet it arrived, whispering not just of brightness, but of a cosmic transition. It's worth remembering that this transition wasn't simply about making the sky visible. It also set the conditions for what would come next. A transparent universe is a connected universe. Light could now transmit information. It could heat interstellar gas, influence star formation, help regulate the balance of matter and radiation. Without that visibility, the universe would have remained closed, a series of isolated pockets. But with transparency came interaction, and with interaction came complexity. In that sense, the completion of reionization was not just the end of the dark, it was the beginning of a cosmic dialogue. Galaxies began to evolve in relation to one another. Light crossed the vast distances between them. Black holes influenced their environments through radiation and feedback. The seeds of large-scale structure, once planted in the quiet of the cosmic dark ages, could now grow in sunlight. Slowly, over billions of years, they blossomed into the interconnected cosmos we see today. And all of this, every galaxy and every photon, is now observable because the fog lifted. It's strange to think that we owe our cosmic awareness to such an abstract transition. No creature witnessed it. No record was kept, except in the patterns of light themselves. But still it happened. A universe once ruled by silence became readable, and for those of us here, floating in one small corner of it, it means that we are not just in the universe. We are part of the visible universe, able to look out, able to listen back, and able to know with quiet certainty that the sky has depth. You might imagine that listening to the early universe would require an impossibly large instrument, a kind of galactic ear pressed to the sky, sweeping vast distances to detect some ancient voice echoing across the void. But the story of one of the most astonishing discoveries in recent cosmology begins not with a massive facility, but with a small, humble radio antenna placed in the red deserts of Western Australia. A simple blade-shaped device lying quietly beneath the sky, patiently listening. This was EDGES, the experiment to detect the global epoch of reionization signature. And in 2018, it may have heard the first whisper of starlight. EDGES was designed to measure the average radio signal across the entire sky, not to create images, but to detect broad changes in the faint glow of the 21 centimetre hydrogen line. This signal, emitted by neutral hydrogen, when the spin of its lone electron flips, is naturally quiet. But stretched over billions of years by cosmic expansion, it becomes even fainter, smeared out, red-shifted down to frequencies the human ear can't hear, but which a well-tuned antenna can. The idea was elegant. As the first stars formed, they would emit ultraviolet light, which would in turn alter the state of the surrounding hydrogen. This change would leave a subtle fingerprint, a dip in the radio signal, centered around a particular frequency corresponding to when those first stars ignited. It would be, in effect, the first visible impact of light on the universe's hydrogen, the moment the silence was no longer pure, and EDGES found it. To the surprise of the astrophysics community, the experiment reported a deep, broad dip in the radio spectrum at a frequency of 78 megahertz, a signature corresponding to a time around 180 million years after the Big Bang. That's earlier than most predictions had dared suggest. It was as if the stars arrived ahead of Virgil, a quiet crowd stepping onto a stage before anyone expected the curtain to rise. But it wasn't just the timing that shocked scientists, it was the depth of the dip. The absorption feature detected by edges was twice as strong as expected. This meant that the hydrogen gas was colder than models predicted, cold enough to absorb more background radiation than anyone thought possible. In simple terms, the hydrogen seemed to be chilled more than it should have been, given the known physics of the early universe. And just like that, a simple antenna in the desert had dropped profound mystery into the heart of cosmology. If confirmed, the Edge's result would be the earliest direct evidence of the first stars altering their surroundings. It would represent the first interaction between light and matter after the long darkness. The first time starlight began to shape hydrogen, not only through ionization, but through resonance. The poetic framing writes itself. This was the first note of the first song. The stars didn't just shine, they changed the air around them. They gave hydrogen a reason to respond, and in that response, a dip appeared. Soft, low, ancient. Yet as with all whispers, the question remains, did we really hear it? Scientific discovery is often painted as revelation, but it is more often a series of careful doubts. As soon as the Edge's result was published, researchers around the world began to scrutinize it. Could this deep absorption feature really come from cosmic hydrogen? Could the instrument have picked up radio interference from satellites, the ionosphere, or even reflections within the equipment itself? The Edge's team had taken extensive precautions, building the instrument in one of the radio-quietest regions on Earth. But even silence can be deceptive. Still, if the signal is real, it raises breathtaking possibilities. One explanation for the stronger-than-expected signal is that dark matter may have played a role. If dark matter interacted with hydrogen in a specific way, transferring energy, siphoning off heat, it could have cooled the gas more than predicted. This would be a profound finding, offering the first non-gravitational interaction between dark matter and regular matter ever detected. On the other hand, if the signal turns out to be a false positive, a product of instrumental error or unaccounted noise, it still marks a powerful moment. It shows that humanity is reaching the threshold of detectability, beginning to hear the earliest parts of the universe's story not with our eyes, but with our ability to listen to temperature, to static, to subtle changes in invisible fields. What makes Edges so powerful as a symbol is not just its findings, but its scale. It's small, modest. It doesn't orbit Earth. It doesn't cost billions. It lies flat on the ground, no taller than a table, wrapped not in gold foil, but in quiet intention. And yet, it may have done what no giant observatory has yet achieved. It may have captured the moment when the dark began to respond. In the desert silence, the first stars spoke. Not in fire, not in colour, but in a dip, a coolness, a change, a line in a spectrum that told us something is happening, and something has always been happening. We're just now learning to hear it. Science, at its heart, is the art of listening, not just to what confirms our beliefs, but especially to what doesn't. Sometimes the universe offers clarity. Other times it offers a soft contradiction, not loud enough to dismiss what we thought we knew, but persistent enough to make us stop, turn our heads, and listen again. The Edge's signal, so seemingly quiet and humble, did just that. It wasn't the presence of something new that startled scientists. It was the absence of expected warmth. The hydrogen gas that filled the early universe was always cold. After recombination, when photons decoupled and the universe became transparent, the gas was left to cool slowly in the absence of light and energy. Over time, it reached temperatures just a few degrees above absolute zero. Still cold, but predictable. That is, until edges. What the Edges team found in 2018 wasn't just the timing of the signal, although that was surprising in itself, but the depth of the absorption. It was too deep, too strong. This meant that the hydrogen gas that absorbed the cosmic background radiation had to be even colder than theory had allowed for. That extra coolness was not in the models, it was not expected, and it was not easily explained. In a field where margins are measured in millikelvin, thousandths of a degree, a discrepancy this size sent ripples across the entire community. If hydrogen was colder than we thought, then something had to be removing energy from it, or preventing it from heating up the way our models predicted. One of the first explanations that emerged, and perhaps the most tantalizing, was that this unexpected coolness might be the first detectable interaction between dark matter and normal matter. Dark matter, up until this point, had only ever made itself known through gravity. It pulls, it clumps, it anchors galaxies. But it has never, not once, not anywhere, been directly observed to touch ordinary matter in any other way. But suppose some theorists suggested that in the early universe, dark matter and hydrogen were close enough, and their interaction subtle enough, that energy could be transferred. Suppose dark matter pulled heat from hydrogen, not violently but gradually, gently, like cold hands drawing warmth from a cup of tea. If this happened, even briefly, it could explain the stronger signal, the deeper dip. It was an idea that felt almost romantic, that the dark matter, long silent, might have whispered once in the cold of the cosmic morning. But science demands more than metaphor. It demands replication. And replication is never easy, especially when the signal is this faint and the noise of Earth is this loud. Radio waves are everywhere. They bounce from satellites, cell towers, planes, and even the ground itself. To hear a whisper from billions of years ago, you must first filter out the shouting of today. To that end, other teams around the world began building their own instruments, each designed not just to confirm the Edge's result, but to do so with even greater precision. One of the most notable is Ceres, the shaped antenna measurement of the background radio spectrum, developed in India. Ceres was built on water, literally floating, to reduce reflections and interference from the ground. It listens patiently from the calm lakes of southern India, away from the cities, tuned to the same ancient signal. Another is REACH, the radio experiment for the analysis of cosmic hydrogen, in South Africa. And there is also LEADER, the large aperture experiment to detect the dark ages, based in New Mexico, USA. Each brings a different approach, a new method of tuning, grounding, isolating, and interpreting the faintest ripples in the radio sky. Together, these experiments form a global network of listening, not coordinated by clocks or commands, but by a shared desire to hear the early universe tell its story, clearly and truthfully. Still, the mystery remains. Is the signal real? Is the hydrogen truly that cold? Did we hear the first star speaking, or did we misinterpret a reflection of our own world? For now, the answer is suspended. The anomaly from Edges has neither been definitively confirmed nor confidently refuted. It floats in that strange space science often occupies, the place between fascination and caution. But perhaps that's where the most honest discoveries live, because the truth is, sometimes it's not the presence of a signal that teaches us the most. Sometimes it's the depth of the silence, the coldness that shouldn't be there, the unexpected dip that speaks more loudly than any spike, like hearing a room go quiet in the middle of a song and realizing something has changed, not because of what was added, but because of what wasn't. In that quiet, we begin to wonder, what if the rules are not wrong but incomplete? What if the silence has texture, and that texture is trying to tell us something? What if the universe is still whispering? but in ways we're only just beginning to interpret. Edges, Saurus, reach, and leader are not answers. They are ears, they are hands held to the glass of time, and whether they hear the signal again or not, they remind us that the past is not gone. It echoes, it puzzles, it waits, and sometimes the silence is too deep, and that's what makes it speak. There are places so quiet that even the wind seems hesitant to pass through. These are the places where humans go when they want to listen to something delicate, something not loud or clear, but ancient, something that does not shout, yet refuses to disappear. The Square Kilometer Array, or SKA, is being built in places like that. In the remote deserts of Western Australia and the plains of South Africa, far from cities, far from power lines, beneath skies that have seen more stars than human footsteps, and its mission is simple, yet extraordinary: to hear what has never been heard before. The SKA is not one telescope. It is a network of thousands. Tiny dishes and low-frequency antennas spread across 2 continents, working together like a single organism. When completed, it will become the largest radio telescope in the world, not in terms of height or mass, but in surface, area and sensitivity. Its name reflects this ambition. 1 square kilometre of collecting area, stitched together from hundreds of thousands of pieces, each tuned to catch a different layer of cosmic memory. What makes SK remarkable isn't just its size, but its design. It will observe the universe in low-frequency radio waves, exactly the range where the 21-centimetre hydrogen line, redshifted and softened over billions of years, still quietly echoes. It is being built specifically to trace these signals across cosmic time, creating a 3-dimensional map of the hydrogen in the universe, stretching from the present all the way back to the cosmic dark ages. Where earlier instruments like EDGES or SARAS aim to detect the average global signal, SK will go further. It will create images, not of stars or galaxies, but of hydrogen itself, the canvas on which all those structures were painted. With enough sensitivity and time, SK will let us see the ripples of density, the ionized bubbles during reionization, and even the first whispers of collapse before any star had lit the sky. This is not seeing in the ordinary sense. It's not visual. It's a kind of auditory cosmology, turning faint signals into maps, into reconstructions, into echoes we can study. It's like pressing your ear to a wall and not only hearing a distant voice, but learning the shape of the house on the other side. This scale will allow us to do more than confirm what we suspect. It will let us see what we didn't know we needed to ask. For instance, one of its major goals is to observe the epoch of reionization in unprecedented detail, tracing how ionized regions expanded, overlapped and reshaped the universe. But it may also catch signals from earlier, perhaps even during the cosmic dawn, when the very first stars were born, and if the signal is clear enough it might stretch even further back into the true darkness, before any starlight at all. In that sense, SKA could become our time machine, tuned not to light, but to the shadows that light left behind. But listening this closely is not easy. The same frequencies that carry these ancient whispers are crowded in modern times, filled with radio stations, GPS satellites, mobile phones, and broadcast signals. Even the tiniest noise from a distant airplane can contaminate the data. That's why SKA's sites were chosen for their radio quietness. In these protected zones, electronic interference is minimized. Researchers are working with governments to preserve radio silence, a kind of technological sanctuary for listening to the sky. Yet even here, challenges remain. The data collected by SKA will be enormous, petabytes per second, so large that entire networks of computers must be built just to process it in real time. Algorithms will scan the sky not once, but thousands of times per second, looking for changes, patterns, and signals buried under noise. And all of it for what? For a line. Oh, spectral fingerprint of a hydrogen atom that flipped its spin 13 billion years ago. A moment of faint energy, stretched and cooled and nearly erased, but not gone. That's the quiet ambition of SKA. It doesn't seek bright explosions or dramatic discoveries. It wants to trace the quiet parts, the scaffolding, the structure, the silences between stars. Because if we can map hydrogen, if we can hear its distribution, its evolution, its response to the first light, then we can reconstruct the hidden history of the cosmos. Not the history of what shines, but of what shaped the things that shine. The history of silence. There's something deeply human about that. This drive to listen past the visible, to collect whispers and piece them together into meaning. The SKA doesn't promise loud answers. It promises detail, depth, dimension. It promises to turn static into memory. And when it finally listens, truly listens, it may not hear words or music, but it will hear structure, coolness, warmth, and transitions. It will hear the universe waking up, and we, standing here so far from the beginning, will finally be able to trace the contours of our own origin, not through stories we tell, but through frequencies we receive, an ear big enough to listen to creation itself, and still humble enough to wait for it. If you were to lie back in a desert, truly far from towns, towers, and glowing windows, you might imagine that you're listening to silence. The stars overhead don't speak. The sand doesn't stir. And yet, even there, under the quietest night sky, you're surrounded by a sea of signals, invisible, incessant, and humming. It's not that the universe has stopped whispering. It's that we, on Earth, have made it very hard to hear. The 21 centimetre line of hydrogen, this delicate fingerprint from the earliest times, doesn't travel loudly. It arrives thin, stretched and weary, having crossed the gulfs of space for billions of years. By the time it reaches us, it is soft, fragile, easily buried under even the faintest interference. And Earth is a place rich in interference. At the heart of the problem is something surprisingly mundane. Radio waves. We use them for everything. Radio stations, cell phone communication, GPS, Wi-Fi, satellites, aircraft, power lines, even cars. All of these technologies pour out electromagnetic signals, often unintentionally, into the sky. And these waves don't fade at the edge of cities. They rise, they scatter, they reflect off the ionosphere and drift across oceans, across borders, across mountains and plains. Even in the most remote regions of the world, some of this noise remains. It's not malicious. It's not even careless. It's just that the same cleverness that lets us send a message across a continent has made it almost impossible to hear a message from a time before continents existed. Consider the ionosphere, a layer of charged particles high in Earth's atmosphere. It bends and bounces low-frequency radio waves, which is useful for long-distance communication. But this same layer also distorts and absorbs the very signals cosmologists are desperate to detect. The 21 centimetre line, when redshifted from the early universe, often lands in a frequency range that is blocked or heavily contaminated by the ionosphere. Below about 30 megahertz, Earth's atmosphere becomes nearly opaque, and even above that, interference from Earth's technology can drown the cosmic signal beneath layers of terrestrial static. For ground-based observatories like EDGES, CERAS and REACH, this is a constant challenge. They must filter, subtract and reprocess their data in elaborate ways to try and extract a faint echo from the overwhelming chatter of the present. And despite all this effort, the data remains uncertain. There are always questions. Was this signal real, or a reflection from a nearby hill? Was this dip cosmic, or just a calibration drift? Did the antenna hear the universe, or did it hear itself? The irony is deep. Humanity has reached a stage of remarkable sophistication. We build telescopes that can peer across the cosmos. We launch spacecraft that land on comets. We bounce lasers off the moon. And yet, in our quest to listen to the first moments of time, we find ourselves talking over them. It's a bit like trying to hear someone whisper in a room where 1,000 people are gently murmuring. No one is shouting, but the sheer number of small voices layered over one another creates a fog of sound too thick to pierce. The signal you want is there. It just keeps slipping through the noise. Scientists have responded with ingenuity. They seek out radio quiet zones, deserts, mountaintops, isolated islands, places where technology thins out. They bury cables, float antennas on lakes, and build shielding to reduce reflections. But even these precautions can only do so much. A single passing airplane, a satellite overhead, even a spark from a faraway power line can leave fingerprints on a day's worth of data. The truth is, Earth is no longer a silent place, and that silence is what we need. The cosmos, in its early ages, was not a loud place either. It didn't shout. It shifted. It cooled. It whispered. The hydrogen line is a record of that whisper, one that has grown fainter with every billion years of expansion. To hear it now, we must stop speaking just for a moment. But here on Earth, that moment may never come. And so we begin to look elsewhere. Not in despair, not in frustration, but in a kind of curious surrender. If we cannot make Earth quieter, then perhaps we must find a place where the quiet already lives. That place, as it turns out, is not so far. It rises above us every night, drifting gently through our sky, not speaking, not broadcasting, simply turning, always showing us the same face, the moon. But before we leave Earth behind, it's worth reflecting on this truth. The interference we struggle with is not a flaw. It is a side effect of our brilliance. The same tools that allow us to send rovers to Mars also create the noise that hides the first stars. The same networks that connect us around the globe are the ones that drown out the messages from a younger cosmos. The challenge is not that we are too loud, it's that we haven't yet found how to listen more softly. Perhaps the answer is not just a better instrument or a quieter location. Perhaps it is a change in how we relate to sound itself, how we design, how we shield, how we create space for silence in a world that rarely stops speaking. Because the universe is still whispering, and one day we might hear it, if only we remember to hush. For centuries the moon has been a mirror for our hopes, a silver circle that reflected not just sunlight, but curiosity, longing, and wonder. Once, we looked up and asked what it was. Then, we asked if we could touch it. Now, with quiet humility, we ask something simpler. Can it help us listen? Because if Earth is a noisy room, then the far side of the moon is the quietest porch in the solar system. There, in the permanent shadow of Earth's broadcast bubble, beyond the reach of FM radio, cell towers, satellites and chatter, there lies a silence so deep it can hold the faintest signals the cosmos has to offer. It is not just empty, it is peaceful. Not just dark, but still. And that stillness is what scientists are beginning to crave. The moon's far side is shielded from Earth's electromagnetic noise by the bulk of the moon itself. It has no atmosphere, which means there is no ionosphere to bend or block low-frequency radio waves. There are no cities, no planes, no phone towers. The signals that reach the far side of the moon do so not by accident or interference, but by age. Waves that have travelled for billions of years, crossing the vast cosmic sea, arriving not in strength but in persistence. This makes the moon an ideal place for what Earth struggles to provide. A clean listening post for the 21-centimetre line from the cosmic dark ages. A growing number of scientists and engineers believe that to truly understand the earliest chapters of the universe, we must leave the noise behind, not far, just far enough. And so the next wave of cosmic exploration may not be about going farther into space, but about going quieter. Several missions are now planned, each one small in scale but vast in implication. NASA, in collaboration with the US Department of Energy and other partners, is preparing Lucy Night, the lunar surface electromagnetics experiment at night. It is not a telescope in the traditional sense, but an instrument designed to operate during the 2-week-long lunar night, when solar interference is minimal. Once placed on the far side, Lucy Night will open its antenna and begin to listen for the red-shifted 21 Sinyaha's signals from the cosmic dawn and the dark ages. It will not take photographs. It will not flash or beep. It will simply sit and wait and record the softest pulses of ancient hydrogen. Another proposed mission is DAPA, the Dark Ages Polarimeter Pathfinder, which aims to orbit the Moon, dipping into the shadow of Earth signals to collect data during its passes. Like Lucy, it will not chase drama. Its mission is patience. Meanwhile, China's Chang'e program, which has already placed landers and rovers on the Moon, has expressed interest in similar radio astronomy experiments. Their Queqiao relay satellite already sits in position to communicate with landers on the far side, a necessary component for any lunar-based radio telescope, since the far side also blocks our communications. Together, these efforts are not about bold flags or giant leaps. They're about something gentler, a collective leaning in, a way of putting our instruments not in control, but in service. Not to make the universe explain itself, but to hear what it's already been saying all this time. Of course, there are challenges. The Moon is not hospitable. Its surface is dry, dusty, pockmarked by ancient impacts. Temperatures swing wildly, hundreds of degrees between day and night. Power must be stored. Instruments must survive in the cold. Everything must be automated, stable, resilient. And because there is no one there to adjust a dial or wipe a lens, everything must be built with extraordinary care, but the reward is equally extraordinary. To place a radio telescope on the Moon's far side is to open a window onto a time we have never seen, not because we lack the tools, but because we lack the quiet. From there, we could finally hear the primordial static that filled space before the first stars. We could detect the structure of hydrogen before galaxies. We could trace the universe's memory, not just through its light, but through its silence. The Moon, in this context, becomes more than a destination. It becomes a reflection of our listening selves, a place where we choose to hush, to wait, and to welcome the quiet as a teacher. And isn't it fitting that we, a noisy species on a noisy world, should turn again to our oldest companion in the sky, not to conquer it, not to escape to it, but to listen with it. The Moon does not speak, but perhaps it can help us hear. The quietest place to hear the loudest story. When we speak of darkness, we often mean it as a void, an absence, a waiting, a nothing, a room before the lamp is lit, a sky before the stars come out. But the darkness that followed the Big Bang was not empty. It was not still, and it was not silent. It was the softest kind of becoming, a quiet that wasn't waiting to be broken, but simply waiting to be seen. The cosmic dark ages, stretching from around 380,000 years after the Big Bang to perhaps 100-200 million years later, are often described as a time when nothing happened. There were no stars, no galaxies, no light in the visible spectrum. But to describe that era in such sparse terms misses its beauty. It wasn't a pause. It was a beginning, slow, deliberate, and deeply profound. In that darkness, hydrogen drifted. Born in the furnace of the Big Bang, cooled by expansion, and now neutral and calm, it filled the universe like a gentle sea. No currents, no waves. Just a smooth, cool fog stretching farther than any eye even now could see. And through it moved something unseen. Dark matter, folding into filaments, weaving scaffolds for the future. Gravity was at work even then. It was pulling, gathering, arranging, not fast, not with spectacle, but with the patience of aeons. Over millions of years, tiny density fluctuations in the hydrogen, so slight they would seem meaningless by any human scale, began to deepen. Regions with a little more matter attracted a little more, then more still. Small differences magnified by time, gently coaxed into structure. There were no stars yet, but the seeds of stars were being planted. There were no galaxies yet, but the framework into which galaxies would fall was forming, quietly, invisibly, like roots growing in the dark before anything blooms above the surface. The darkness was not empty, it was pregnant with structure. It's easy to romanticize this period, to speak of it as a womb for the universe's future brilliance. But this isn't metaphor alone, this is what the data shows. When we look at the cosmic microwave background, we see tiny fluctuations, imprints of temperature and density left over from recombination. These are the fingerprints of the initial conditions, and when we simulate how those fluctuations evolve under gravity, they become the web of galaxies we see today. Everything, every star, every planet, every cell, began as a ripple in that darkness. And yet, because there was no light, we often skip over this era. We imagine the universe as beginning with brightness. But in truth, it began with potential. You could think of it like a theatre before the play. The stage is set, the actors are in costume, the script is written, the audience is hushed. And yet the light has not risen. There is no action, only intention. But in that intention lives the entire performance. So it was with the early universe. The act of becoming had already begun. Even the name Dark Ages feels slightly unfair, a term borrowed from human history, meant to suggest ignorance or stagnation. But cosmologically it was neither. There was no ignorance. There was only evolution. There was no stagnation. There was the slow breathing in before the cosmic exhale. The silence was not silent. It just didn't speak in light. It spoke in gravitational potential, in quantum fluctuations, in the smooth tension between inertia and attraction. It was a universe not waiting to begin, but already beginning, just in ways we didn't yet know how to see, and now we do. Through simulations, through the 21 centimetre line of hydrogen, through careful modelling of structure growth, we are starting to piece together what that darkness held. It is no longer a void, it is a story. And like all stories, it began before the first word was spoken aloud. So perhaps the term Dark Ages should not suggest emptiness, but privacy. A time the universe kept to itself. A chapter it did not illuminate, but one it wrote in silence. And now, like readers in a quiet room, we are learning to turn those early pages. Not with our eyes, but with instruments that can feel the weight of structure in the dark. It wasn't waiting to begin. It was the beginning. There is a strange kindness in light, not because it illuminates, not because it dazzles or reveals, but because it remembers. Every photon that reaches your eye carries a journey, a silent, unwavering line stretching backward through time, untouched by the moments it passed through, unchanged by the ages it crossed. It doesn't age, it doesn't tire, it simply travels, holding on to the moment it was born until it touches you. And so when you look up at the sky, not just in poetry, but in physics, you're looking into memory, not yours, not humanity's, but the universe's memory. Wavelengths stretched across time, each one an ancient story told in motion. You might be sitting now in a room lit by electric bulbs, a cup of tea in your hand, a blanket over your legs, and it's easy to think the past is far away. But it's not. It arrives constantly. It moves through the walls, through the windows, through the soft fabric of the air. Starlight from long dead suns, microwave whispers from a time before galaxies, radio pulses that began their journey when Earth was a molten sphere. All of it still arrives, still present, still here. And in the silence, it speaks. Not in words, but in persistence. That's what light does. It remembers. You're not separate from that memory. You're its child. The atoms in your body, carbon, nitrogen, oxygen, iron, were forged in stars. But the hydrogen? That came first, before stars, before galaxies, before time had any structure. The hydrogen in your water, in your breath, in the proteins that hold your cells together. It was born in the first minutes after the Big Bang. It survived the cosmic dark ages, untouched, waiting. It flowed through the early universe, collapsed into stars, fused into heavier elements, and found its way back into dust, into clouds, into planets, and into you. You are, in a very quiet way, a vessel for the universe's oldest material. And that makes you a listener too. Because when telescopes tune to the sky, when they trace hydrogen's 21 centimeter line, or chase the stretched pulse of light from a dying star, they are not discovering new things. They are listening to what has always been true. They are learning how to read a story that was already written, not in pages or ink, but in wavelength, temperature, motion, and time. And what they find is that the universe doesn't forget. It doesn't erase the past. It stores it. Every light wave we capture today is a note from before, a gentle reminder that time moves only one way for us, but not for the particles it carries. To a photon, the journey is instantaneous. To us, it is a gift delayed. That's the curious thing about perception. We think of light as being fast, but it's not just speed that makes it powerful. It's its persistence. It holds on to what it was, and it delivers that truth to anyone patient enough to receive it. In this way, you are more than a being made of matter. You're a meeting point where ancient hydrogen, starlight, and curiosity intersect. You're made from the things you wonder about, and you are capable of understanding them, not because they are simple, but because you carry them inside you. The universe, in its strange and long unfolding, did not keep you separate. It folded you in, into its gravity, into its chemistry, into its story. And that story is not just one of brightness, it is one of remembrance. We often think of the memory as something brains do, but the universe remembers too. Not in neurons, but in structure, in radiation, in the long echo of its first actions. It remembers in hydrogen lines. It remembers in microwave ripples. It remembers in the composition of your bones, and in the way your eyes can see starlight, your ears can hear music, and your mind can ask questions no other species, as far as we know, has ever thought to ask. You're not outside this memory. You are one of its ways of remembering. The photons that touch your skin tonight may have left their stars when dinosaurs walked the Earth. Some may have come from galaxies so far away that their light began travelling long before Earth formed. And you, in the quiet of this moment, are the final destination of their impossible journey. You don't need to do anything special. You don't need to understand every formula or memorize every term. All you need to do is be here. Be here and know that you are a listener. You are the soft landing for light that refused to be lost. You are made of hydrogen, touched by time, illuminated not just by stars but by questions. You are, in every sense, a small remembering of the cosmos. There's something soothing about the thought of a photon, not because it's small or fast or even ancient, but because it arrives. It finishes its journey. Across billions of years and uncountable distances, through expanding space, through clouds and clusters, around galaxies and through voids, it continues. And then, one day, or one night, it reaches you. It does not rush. It does not falter. It carries its memory with grace. And when it touches your telescope, your retina, your skin, it has not changed. It is still what it was, a messenger, a remnant, a whisper from the beginning. That whisper has travelled longer than any civilization has existed. It has moved through a universe that has changed shape, density and temperature countless times, and yet it comes bearing the original tone of its birth. Whether from a young star or a cold hydrogen cloud, or even from the plasma that filled the universe before atoms existed. And now, in this moment, it rests. That idea alone is enough to soften the breath. Not everything that travels long becomes loud. Some journeys end not in explosion or applause, but in stillness, in arrival, in quiet touch. You're surrounded by such arrivals, all the time. In every room, in every moment of night, light that began long before Earth had continents is still arriving. Cosmic microwave background radiation, stretched thin and cool, permeates the air. You can't see it, you don't feel its warmth. But it's here, a glow so ancient, so gentle, that it has become part of the silence. That glow is the residue of a universe finally cooling enough to let light go free. And in that freedom, a kind of forever began. Because light, once released into space, rarely stops. It rarely forgets. It simply continues, and in doing so, it preserves a time no longer accessible in any other way. And so it is with the 21 centimetre line of hydrogen, a line that hums quietly through everything, almost too faint to notice. It's not a line of drama. It's not the bright flash of a supernova or the violent wave of a black hole merger. It is steadier than that, more patient. It is the quiet signature of atoms just being, spinning, flipping, releasing a breath that takes billions of years to reach an ear that finally knows how to listen. Perhaps that's why the universe has always felt like a kind of lullaby, not because it's boring or slow, but because it teaches us that slowness is not emptiness, that quiet is not lack, that long journeys don't require noise. And perhaps that's why this entire story of darkness, of light, of hydrogen and time feels best when it ends not with a revelation, but with a resting point. The dark wasn't broken, it bloomed. It wasn't a problem to be solved, it was a process, unfolding, stretching, structuring. And through it all, silence was not absence. It was instruction. It taught structure. It guided collapse. It set the stage for everything that would glow later, and everything that would wonder about the glowing. Even now, as scientists build telescopes, as data flows across cables and computers hum through the night, what they seek is not something new. What they seek is a memory that never left, a frequency that waited softly until we learn to ask a better question. And you, in this moment, are part of that question. Not just a listener, but a vessel. Not just a student of science, but an embodiment of what it describes. You're made of the same hydrogen that once floated through that dark, unlit sea. You are shaped by forces older than the Earth. You're one of the few parts of the universe that has become conscious, and one of the few that has learned to listen back. So sleep, little photon from the deep. Your journey is finished. Sleep, quiet hydrogen shaped by silence. Sleep, long wave stretched thin by time. Sleep, small echo from a vast beginning. And to you, listening now, may your rest be just as patient, just as peaceful, just as filled with structure, quietly preparing to become light. Because the story hasn't ended, it has only reached you. And here, in this breath, in this moment of stillness, you are the continuation. You are the place the cosmos paused to remember itself. Sleep well. The universe remembers you.